Welcome to an exploration of one of fluid dynamics' most puzzling phenomena, anomalous mixing in chaotic micromixers. Chaotic micromixers generate complex swirling patterns designed to mix fluids rapidly at microscale, yet reality defies our theoretical predictions. Let's begin by understanding what chaotic micromixers are and why they matter. Chaotic micromixers are microscale devices that use specially designed geometric features to create chaotic flow patterns. Fluid enters the channel and encounters obstacles that stretch, fold, and twist the flow, creating exponential separation of nearby fluid elements. These devices are critical for lab-on-chip systems, chemical reactors, and biomedical diagnostics where rapid mixing at small scales is essential. The Péclet number governs the competition between advection and diffusion in these systems. The Péclet number equals velocity times length scale divided by diffusivity, where U is the characteristic velocity, L is the relevant length scale, and D is the molecular diffusivity of the species being mixed. Physically, Péclet number represents the ratio of advection rate to diffusion rate. At low Péclet numbers, diffusion dominates and mixing occurs readily. At high Péclet numbers, advection dominates, and we must rely on chaotic stretching to thin fluid filaments until diffusion can act. Let's calculate a typical Péclet number for a micromixer to understand the regime we're working in. Consider a typical micromixer with velocity of 1 millimeter per second and channel width of 100 micrometers. For small molecules in water, the diffusivity is approximately 10 to the minus 9 square meters per second. Calculating 10 to the minus 3 times 10 to the minus 4 divided by 10 to the minus 9 equals 100. A Péclet number of 100 means advection is 100 times stronger than diffusion, so we absolutely need chaotic stretching to achieve mixing. Theory predicts that chaotic flow should produce exponentially fast mixing. Let's see what should happen. In chaotic flow, nearby fluid elements separate exponentially fast, characterized by the Lyapunov exponent. The Lyapunov exponent lambda equals 1 over time times the natural log of final separation divided by initial separation. Separation grows exponentially with time, meaning fluid interfaces stretch exponentially, thinning concentration gradients rapidly. The mixing time should scale as 1 over lambda times the natural log of Péclet number. For Péclet 100 and Lyapunov exponent 1 per second, we expect mixing in about 4.6 seconds. But experiments reveal something unexpected and troubling. Experimental measurements consistently show mixing times 10 to 100 times longer than theoretical predictions suggest. The discrepancy is dramatic. What should take 5 seconds actually takes 50 to 500 seconds in practice. When researchers back-calculate effective Péclet numbers from mixing data, they find values much lower than the actual flow conditions suggest. This raises a critical question. What hidden mechanism is preventing the expected chaotic mixing? The answer lies in subtle coherent structures that persist within the seemingly chaotic flow. Coherent structures are special regions in the flow, where chaotic mixing is dramatically suppressed. Think of coherent structures as islands of regular motion, embedded in a chaotic sea. Fluid trapped near these islands mixes extremely slowly. These include elliptic islands around periodic points, KAM tori that are impermeable barriers, and partial barriers called cantori. Let's understand the physics of why these structures so effectively resist mixing. Fluid elements near coherent structures experience minimal stretching because they follow quasi-periodic orbits rather than chaotic trajectories. The local Lyapunov exponent near these structures is approximately 0, meaning no exponential separation occurs. Fluid circulates around these islands in closed loops, remaining trapped and poorly mixed, while the surrounding chaotic region mixes efficiently. For material to escape these structures, it must diffuse across stable manifolds, a painfully slow process at high Péclet numbers. We can describe these transport barriers mathematically using dynamical systems theory. The flow is described by these ordinary differential equations for particle trajectories, where u and v are velocity components. Fixed points and periodic orbits of this dynamical system create the organizing structures around which coherent regions form. The Jacobian matrix J describes local flow deformation and identifies elliptic versus hyperbolic behavior. Elliptic fixed points have purely imaginary eigenvalues, creating closed orbits and stability islands that trap fluid. We can quantify the impact of coherent structures through an effective Péclet number. The effective Péclet number equals a reduction factor F times the nominal Péclet number. The reduction factor F depends on what fraction of the flow domain is occupied by poorly mixed coherent structures. If phi is the fraction of area in coherent structures, mixing efficiency drops roughly as 1 minus phi squared, showing quadratic degradation. Even if only 10% of the domain contains coherent structures, mixing can be reduced by a factor of 5 or more. Let's work through a concrete numerical example demonstrating the anomaly. Consider a micromixer with channel width 200 micrometers and flow velocity 2 millimeters per second. The Péclet number is 400, indicating strong advection dominance. With Lyapunov exponent 1 per second, theory predicts mixing in about 6 seconds. But experiments measure mixing time of 90 seconds, a factor of 15 discrepancy. The effective Péclet number is only 27, about 15 times smaller than expected. This large reduction implies approximately 20% of the flow domain is occupied by mixing-resistant coherent structures. How do we actually detect these hidden coherent structures experimentally? Poincare sections, which plot particle positions at regular time intervals, reveal the island structures embedded in chaos. Islands appear as closed curves of points, while the chaotic region fills space densely, making the structures visually obvious. Finite-time Lyapunov exponent fields compute local stretching rates and highlight transport barriers as ridges of low stretching. Experimental fluorescent dye visualization directly shows unmixed pockets that persist far longer than theory predicts. Let me offer an intuitive analogy that makes this phenomenon more tangible. Imagine stirring cream into coffee. Most cream gets stretched into beautiful spirals and mixes quickly. But there's always that stubborn blob near the center that refuses to mix, spinning in place like a coherent structure resisting chaos. That persistent central blob is exactly analogous to coherent structures in micromixers, sitting in a stable region where stirring has minimal effect. Understanding anomalous mixing has profound practical implications for device design. If designers assume theoretical mixing times, they'll undersize devices, leading to incomplete chemical reactions and poor product quality. In drug delivery applications, unmixed regions can cause dangerous non-uniformity in delivered doses. The order of magnitude discrepancy between design assumptions and reality can cause catastrophic device failure. Medical diagnostic tests, relying on rapid mixing, may give false negative results when coherent structures prevent reagent contact. Engineers have developed several strategies to minimize the impact of coherent structures. Introducing time-periodic changes to the flow can break up stable islands by preventing particles from settling into periodic orbits. Moving to truly three-dimensional flows prevents the formation of two-dimensional invariant structures that trap material. Alternating obstacle patterns or switching flow directions can destroy coherent structures by making the dynamics non-autonomous. Using multiple mixing stages in series gives trapped fluid multiple chances to escape coherent regions. Diffusion plays a critical role in transport across the boundaries of coherent structures. The advection diffusion equation shows the competition between diffusive spreading, represented by d nabla squared c, and advective transport. Near transport barriers, diffusion must work against the stretching flow to move material across the boundary. The escape time scales as L squared over d times a function of the local Lyapunov exponent. Material must slowly diffuse across the barrier boundary, with the rate limited by both the diffusion coefficient and the barrier strength. For Péclet 400 and a barrier thickness of 10 micrometers, the escape time by diffusion alone is about 40 seconds, explaining slow mixing. Modern analysis uses Lagrangian coherent structures to identify transport barriers rigorously. Lagrangian coherent structures are defined as ridges in the finite-time Lyapunov exponent field computed from flow data. The finite-time Lyapunov exponent equals 1 over t times the log of the square root of the maximum eigenvalue of delta transpose delta. High FTLE ridges appear as sharp boundaries that organize the flow, showing where material separation is most intense and barriers exist. The LCS framework provides a rigorous objective method to identify and quantify transport barriers in complex flows. An important question: Can we predict the degree of anomalous mixing from the mixer geometry? The answer is yes, partially. By analyzing the flow's dynamical systems properties, we can estimate coherent structure locations. We compute fixed points and their stability from the velocity field to locate potential islands. Fixed points satisfy velocity equals 0, and we examine eigenvalues of the Jacobian at these points. Elliptic fixed points predict where islands will form and their approximate sizes based on the eigenvalue magnitudes. This predictive capability allows engineers to optimize mixer designs computationally before expensive fabrication. Researchers have derived scaling laws that describe how anomalous mixing depends on system parameters. Mixing timescales as L squared over D times Péclet to the power negative alpha, where alpha depends on coherent structure fraction. For ideal chaotic mixing with no coherent structures, alpha equals 1, giving the classical scaling. But with significant coherent structures, alpha drops to 0.3 to 0.7, indicating much weaker Péclet dependence. On log-log plots, ideal mixing shows slope -1, while anomalous mixing shows shallower slopes, revealing the inefficiency. Recent experiments have directly confirmed the presence and impact of coherent structures. Microparticle image velocimetry experiments in herringbone mixers directly visualize persistent unmixed pockets lasting 10 times longer than expected. Particle tracking experiments demonstrate anomalous diffusion near transport barriers, confirming the role of coherent structures in hindering mixing. In conclusion, chaotic micromixers, despite their promise for efficient mixing at the microscale, often fall short due to the presence of coherent structures that resist mixing. Understanding and predicting these structures is crucial for optimizing device design to minimize their impact and achieve efficient mixing. Advancements in diagnostics, such as Lagrangian coherent structures, and simulation tools will be key to overcoming the challenge of anomalous mixing in chaotic micromixers.